Hello friends, welcome to engineering tutorial. So far we have discussed about the various concepts related to electric field, electric potential, and previously we discussed about the important concept in electrostatics, which is Gauss law. So in this video, or the next few videos, we'll be discussing about an important application of Gauss law, which is to determine the electric field due to a charge configuration. Okay, so we'll discuss various configuration of charges, and here we'll be using the concept of Gauss law to determine the electric field due to that charge configuration. So the first concept which we'll be discussing is the electric field due to a line charge, infinite line charge, through the application of Gauss law. So just a quick review. So we know electric flux is the number of electric field lines passing through an imaginary surface. So here the area vector, or the surface area vector, and the electric field vector, and the angle between them, E vector, ds vector, and theta, that plays a role. Electric flux is the closed surface integral of the dot product of electric field and surface area vectors. Okay. Then Gauss law, the statement of Gauss law is that the total electric flux, that is the total number of electric field lines passing through any closed surface, is equal to 1 by epsilon 0 times the net charge enclosed by that surface. Okay, this is one way of writing electric flux, and this is the other. Okay, this is one way and this is the other. First or second, okay, whichever way you can write, we will get the same result. But here we will be equating these two things, okay, these two mathematical expressions, to determine the expression of electric field. Our main objective here is to calculate the expression for electric field due to various charge configuration. So this is one of the most important applications of Gauss law, which is to write a relationship between electric charge and electric field, or express electric field in terms of the charge configuration, or the charge contained in within the closed surface. So here the concept of Gaussian surface comes into play. Like I said in the previous video, a Gaussian surface is an imaginary surface, okay, a hypothetical closed surface which is chosen appropriately, suitably, so that it entirely covers the charge configuration which we are taking into consideration. So depending upon the different charge configuration, the shape and size of the Gaussian surface will be different. So the main requirement is that the imaginary Gaussian surface should fully cover the charge configuration which we are considering. Okay, so this is the electric field due to a line charge. So let us understand what is the situation here. We have a very thin wire. You can imagine a very thin wire, okay, and it is very long, covering infinite distance from this side and to this side. We have just considered a certain section of that thin wire. It is positively charged. It has a linear charge density lambda, okay, lambda coulomb per meter. This is linear charge density, okay, and it has a length L. We have considered a certain length, arbitrary length L of the wire. okay, this. So we have to determine the electric field at this point P, okay, electric field at this point P, which is at a distance of r, perpendicular distance r from the wire. So here we have to choose a suitable Gaussian surface so that it fully covers the entire linear charge configuration. Linear charge configuration because it's a straight wire where it is the positive charge is uniformly distributed. Okay, uniformly distributed with linear charge density lambda coulomb per meter. So here the Gaussian surface which we have considered is the cylindrical one. So we have considered an imaginary cylinder of the same length L as the length of the cross section of the section of the wire, and the radius of the cylinder is r, which is the distance of the point P where we have to calculate the electric field from the wire. So here the Gaussian surface, okay, the Gaussian surface is an imaginary cylinder with radius equals to r and length equals to L. This is the Gaussian surface. It's imaginary, hypothetical, so that it fully covers the wire. Now, here the concept of the angle between the electric field vector and the surface area vector will come into play. Here, this whole cylinder, the imaginary Gaussian surface, it consists of two parts. Okay, it consists of two parts. First is the two end caps, the circular cross sectional end caps at the two ends, the left and right. Okay, this is the end cap, this portion. And then we have is the cylindrical portion, this portion. This is the cylindrical portion and this is the circular end cap portion. Okay, so I'm using a different clean diagram to start again. So this is the cylindrical portion and this is the end cap circular portion. So the flux, total flux will be because of the end caps, the two end caps, and the electric flux due to the cylindrical portion. That will be the total electric flux. Okay, so pay attention again, this is a clean one. So here if we focus on the end caps, okay, I'm trying to visualize a three-dimensional situation, a two-dimensional picture. So this is the end cap. We know that the electric field lines, they are always directed away from a positive charge. They are always directed away from a positive charge at each point. Okay, the electric field lines are always directed away. Here also like this. Okay, so here if we consider here at this point, okay, at this point, this particular point, this is the electric field, okay, directed upwards, and the area vector at this small point, this is the small area ds vector, it is in the mutually perpendicular direction as compared to E vector, the electric field vector. This is infinite wire, isn't it? Here also it is positive charge, positive charge, positive charge. Here also it's positive charge. We have just taken a small section of it. Okay, we have taken a small section of it. It doesn't end here. It continues. continues from here, there is also positive charge, positive charge. We have just taken a small section. So at each point the electric field is directed away. But for this two cross sections, the area vector is directed in mutually perpendicular direction. Okay, ds vector, and here also ds vector, like this, mutually perpendicular direction. For the end caps, electric field vector is perpendicular to the area vector. We know that the area vector is always directed outwards normally to the surface. Okay, we know that that we have discussed in electric flux, that the area vector is always directed outwards. So let's say if we have this area, the area vector will be directed in this directions. If we have a tilted one like this, the area vector will be directed in this direction. Suppose we have area like this, the area vector will be directed outwards normally. Okay, this is the concept of area vector, where the length of the vector will be directly proportional to the magnitude of the area and the direction will be outwards normally, perpendicularly. So here for the end caps, E vector is perpendicular to ds vector, that is the angle between E vector and ds vector is 90 degree. Okay, now for the cylindrical portion. For the cylindrical portion, at each point, let's say at this point also, this is the area vector like this, and the electric field vector is like this, in the same direction. Okay, in the same direction. Here also, if we consider, again I am trying to visualize a three-dimensional thing in a two-dimensional picture. So here also, let us consider this point in the you imagine as if the vector is coming towards you, the arrowhead is coming towards you. This is the positive charge. Imagine the vector is coming towards you, pointed towards you, like an arrow coming towards you. So it will be in this way, outwards. Also the area vector will be like this. Here also, if we consider it at certain angle, the electric field will be in this direction, also the area vector will be in this direction. This is the electric field vector, and the area vector will also be in the same direction. So for the cylindrical portion, okay, for the cylindrical portion, E vector, and that is the electric field vector and the surface area vector, they are in the same direction. So angle between them is 0 degree. Okay, angle between them is 0 degree. Here also, if we consider this area, this portion here, this is the area vector, and here if we consider this point, the electric field line will be like this, E vector, and this is the ds vector. They are along the same line. For any point here on this cylindrical portion, we will find a spot on the wire where the electric field vector will be along the same line, directed as compared to that surface area vector. Okay, so for the cylindrical portion, E vector and ds vector, they are in the same direction. And why I am saying that the E vector will always be outwards? Because for the end caps, the wire doesn't end here, it continues. So electric field will never be in this direction. It cannot happen because the wire is not ending. We have just taken a small section of the wire. Okay, so we'll only have the cylindrical portion where E vector and ds vector are in the same direction, and for this imaginary end caps, E vector and ds vector, the angle between them will be 90 degree. So now we have to apply the concept of Gauss law and electric flux. So for the end caps, all points on the end caps, okay, for all the points on the end caps, Okay, all the small points on the end caps. Any number, and there will be infinite number of points for all the points on the two end caps at all the end points. Okay, the angle between the electric field vector and the area vector will always be 90 degree. Okay, the angle will always be 90 degree. Okay, this is the electric field direction. Here also ds vector, it is 90 degree. Here also it is 90 degree. For this also it is 90 degree, because the electric field will also be in this direction downwards, like this electric field line. So here also it will be 90 degree. This is also 90 degree. Like this it will be for all the points on the end caps, the angle will be 90 degree. So if we apply the concept of electric flux, that is the surface integral of E vector dot ds vector will be 0, because it is the dot product, that is E ds cos 90 degree, which is equal to 0. Angle between them is 0. So for all the points on the left and the right end cap, the electric flux is 0. No electric field lines are passing through the end caps. Now for the cylindrical portion, okay, now for the cylindrical portion, this portion, like I explained, the angle between E vector and ds vector for all the points on the cylindrical surface, they are in the same direction, 0 degree. So for the cylindrical portion, the electric flux is equal to, again, the closed surface integral of the electric field vector and the surface area vector, which is equal to E ds cos 0 degree. Now an interesting thing, if you see all the points on this entire cylindrical cross sectional area, all the points on this cylindrical cross sectional area here, okay, imagine this is a three-dimensional thing, okay, three-dimensional thing. All the points on this cylindrical cross sectional area, they are at the same distance from the wire, okay, they are at the same distance from the wire, which is equal to r. All the points, they are at the same distance from the wire. Here this, okay, all the there, it is the radius of the wire, they are at the same distance. Okay, this is a three-dimensional thing. Okay, I am trying to explain it in a 2D picture. So all the points, they are at the same distance from the center, okay, where the straight wire is present. So as r is constant, as the distance of the wire from all the points on the cylindrical cross-sectional section, the area is constant, so electric field will also be constant, because electric field is equal to q by 4 pi epsilon 0 r square. Okay, as r is constant, okay, as r is constant, then E will also be constant. Okay, the magnitude of electric field will be constant. Its direction may be different, but the magnitude of electric field will be constant, because the magnitude of r, that is the distance of the point on all the points on the cross-sectional cylindrical cross-sectional area from this wire, it is constant. Okay, all the points here and here, like this. So E is constant. So that's why here E goes outside, because it is constant, and we only perform the closed surface integration of the area. Now we know that the area, surface area of the cylindrical section is equal to 2 pi RL. Okay, we know that the curved surface area of a cylinder, 2 pi RL, where we have, let's say, a cylinder of radius r and length L, the surface area of the cylindrical section, that is equal to 2 pi RL. Okay, so this is E into 2 pi RL. For the cylindrical section, the electric flux is equal to E into 2 pi RL. Now we know, as per Gauss law, okay, as per Gauss law, the electric flux through any imaginary Gaussian surface, in this case a cylindrical Gaussian surface, is equal to the net charge enclosed by that surface divided by epsilon 0, absolute permittivity. So now here the net charge enclosed by that surface, this the charge configuration, which is a length L of the wire with linear charge density lambda, okay, linear charge density lambda. It has a linear charge density lambda. So the net charge enclosed by this cylindrical cross section, that is equal to Q net is equal to lambda L. The net charge is equal to lambda L, because linear charge density of this wire is lambda coulomb per meter. So for every 1 meter there is lambda coulomb charge placed on it. So for L length of the wire, L meter of the wire, with the charge enclosed by the imaginary Gaussian surface, that is equal to lambda L. Okay, the charge enclosed by this imaginary cylindrical Gaussian surface, that is equal to lambda L. So we'll put that value here. Okay, we'll put that value here. So E into 2 pi RL is equal to lambda L by epsilon 0. Okay, now here L will get cancelled, both sides L and L. So we have E, that is the electric field, the expression of electric field, that is equal to lambda by 2 pi epsilon 0 R. Okay, lambda by 2 pi epsilon 0 R. Newton per coulomb or volt per meter, whatever it is, we can take. Okay, so this is the expression of electric field due to an infinite line charge with linear charge density lambda at a distance r from the wire, perpendicular distance r from the wire. So the same thing, it will be lambda by L by epsilon 0. So the electric field, that is equal to lambda by 2 pi epsilon 0 r. This is the final expression. Okay, for electric field intensity due to linear infinite length of wire with linear charge density lambda. Okay, this. So this is the situation that we have here. See, this is the thin long wire which is positively charged. Okay, it is positively charged wire with linear charge density lambda, positively charged wire. Okay, this one, and this is the cylindrical Gaussian surface. So let us try to see. If we rotate this like this, see, the wire is passing through it. This is the thing here. Okay, let's just try to bring it a little bit towards the center. This is positively charged wire. Okay, this is positively charged wire, and from the Gaussian surface, okay, it is at a distance r away from it. Okay, and there lies a point on the Gaussian surface where we have to determine everything. So obviously the electric field lines, they are directed away from the positive charge in all directions. This this, this, like this. In every direction, infinite number of electric field lines will be there. Okay, and again let us try to rotate it. So because of that, at each point on the Gaussian surface, the cylindrical Gaussian surface, if we take any area, any small area here, any small areas here, the surface area vectors will be it will be coming towards you. Imagine as if you are sitting in front of the screen and the electric field vectors will be pointed towards you, same as in the direction of the electric field. Again, let us try to understand it. Again, let us rotate it. So the electric field vectors will be, see, imagine these, just make a mental note of where the points are located. So here, if I draw the surface area vectors, marker, okay, if you draw the surface area vectors, it will be like this. Let's use a different ink. Okay, same, in the same direction as the electric field vectors, like this. So there will always be two pairs, that is an electric field vector and the area vector, which will always be in the same direction for this cylindrical cross section. While for the end caps, this is the end cap, again let us rotate it. For the two end caps, these end caps, see, for this end caps, here there is a positive charge, infinite wire, so there is a positive charge here, so it will always be, the electric field will be like this. So for the end caps, for these end cap, the entire this end cap region, if we take any number of areas, it will always be like this. The area vector will be like this, outwards. ds vector, it will always be perpendicular to the electric field lines. For both the end caps, it will always be 90 degree. Whereas for the cylindrical portion, the direction between the electric field vector and the area vector, it will always be 0. Okay, so this is the situation. Okay, so this is the first charge configuration that we have discussed. Certain length of wire with linear charge density lambda, and we have considered a cylindrical Gaussian surface. In the next series of videos, we will be discussing other charge configuration. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.